We know there's a virtual network interface card inside of our UCS design. And one of the things that we're going to show you how to do is to go ahead and virtualize things like MAC addresses. So this is something that we're going to emphasize beginning in chapter 6, where we go in and we say, okay, we're going to take pools of MAC addresses. We're going to have the UCS system create pools. It'll help us do this. Create pools of available identifiers that it can use to virtualize these devices and their placement. Understand that in the UCS system, we want to virtualize things like MAC addresses so that if we have an underlying hardware failure, we can go ahead and take everything, the apps, the operating system, and vMotion it, migrate it from one blade to another. And obviously we want the MAC address and everything to stay consistent so that there is no confusion in our security infrastructure and with the application itself. So this is going to be critical that we virtualize everything for the environment. And Pete says, yeah, that's live migration in Hyper-V. And Pete, thanks so much. One of the inadequacies that I possess, and I admit so readily, is that I am pure VMware with my software experience when it comes to virtualization. We are going to be releasing courses here at stormwind.com regarding Microsoft's solution. We're even talking about releasing courses in Citrix's solution, and I can't wait for those. I'll be one of the first people to sign up for those courses because I am biased through my experience with VMware. Okay, so VMAC, virtual NIC and virtual MAC address portability, something we definitely need to have, and we are going to show you how to set that up. By the way, for you storage area networking people, you're saying, well, what about worldwide names and worldwide port names? I need those virtualized as well. And yes, don't worry, all of that can be virtualized in the UCS system as well, and we'll show you how to do that. All right. Well, earlier we said that the input-output module supports in the current generation. Let's call this course the current generation. We know there's some newer generation technologies, but we know in what we'll call the current generation of technologies, the UCS manager supports those 3-link topologies, right? The 1-link, the 2-link, or the 4-link topologies. And we know that the mezzanine card inside the Blade server has the 110 gig connection. So what we're going to do is we're going to, like we talked about, the UCS system is going to be dynamically, on its own, pinning these virtual MAC addresses to particular uplinks. Okay, we know this is going to take place by default. This is an exam question, not to give too much away here, but as you might guess, this is a key point in the exam. That with you doing nothing at all, no administrator intervention, the UCS system runs in that end host virtualization mode that we talked about. MAC addresses, virtualized MAC addresses from the server blades are going to be pinned to particular uplinks. And that's how the multiple uplinks are going to be utilized. And there's no spanning tree running. And obviously, if there's a failure, we need to talk about what's going to happen to the particular pinnings of those MAC addresses to uplinks. Now, first of all, let me prove to you what we just talked about. We need to prove that there is this automatic pinning that takes place. So we're going to prove this in a pretty cool way. We're going to go to that read-only shell for the Nexus OS, right? So notice here we go connect NX OS. And once we get into that Nexus OS shell, I'm going to say show run interface E1/1/1. This is our first chassis, our first slot, our first server. And it shows us the running configuration for that particular interface. And it says pinning server. And it says the fabric interface is E11. And if we go and look at that particular configuration with show run interface E11, we see the pinning server command, which causes this particular pinning behavior right by default. So, we know we have we typically target multiple input-output module links to the Fabric interconnect, right? If we have the loss of one of those links, we would have a loss of connectivity for servers that are pinned to that link. But the great news is, what we will typically configure is NIC teaming in the operating system that's running virtually, or we'll do hardware-based failover as part of our service profile, which we'll teach you how to do. And this means that when there's the loss of a link, we fail over to the Fabric Interconnect B. All right, now let's take a look at the high availability, the typical high availability configuration here with our 4-link topology. So notice we're dealing with our 4-link topology. So it's funny because the IOM doesn't support a 3-link topology, but notice the 3 active links will now continue to forward traffic until there's a re-acknowledgement of the chassis. Let's say there were 2 servers that were pinned to the failed link. Remember, they will be down. They lose connectivity unless we've done NIC teaming inside the VMware, for instance, or we've configured the service profile for our Fabric failover. By the way, if we re-acknowledge the chassis, the input-output module will now form a 2-link topology and re-pin the blade servers as part of the 2-link topology. By the way, we'll now have those servers that failed over to the B fabric reconnected to the A fabric. So this is pretty complex. And this may be something that you need to, really examine and study for a bit. But the bottom line is, the great news is, obviously here, is that through the high availability configuration, either done at the operating system level with NIC teaming, or through the fabric interconnect redundancy through the multiple fabric interconnects in the UCS, when there is a failure of one of these key links, one of these key server links, thanks to these high availability options that we can configure, there's no loss of connectivity. Obviously, there could be if we didn't have the high availability configured correctly. All right. Obviously, this is something that's real important for UCS administrators to think about. The general rule is, if we have one of these input-output module links fail and the servers aren't configured for the high availability, we want to re-acknowledge the chassis as quickly as possible. Okay? So we need to re-acknowledge if our servers aren't configured for the appropriate failover. If our servers are configured for the appropriate failover, then we are not obsessed with re-acknowledging the chassis. Because all we have to do in this case, if our servers are configured for the failover, all we've got to do is replace the link. And then notice, once we replace the failed link, we'll have automatic failback. So we restore the link is identified by the UCS system, and servers are going to do what's called failback to the appropriate links. All right. Now, let's not confuse IOM pinning, which is what we were just talking about, with uplink pinning. Yeah. Notice we got to be very careful with our words here. So we were just talking about server port or IOM pinning, and now we want to distinguish that between uplink pinning. Uplink pinning is where we are going all the way through the infrastructure, right? We're going from the server max all the way up and pinning those to particular uplinks. How does this work? Well, by default, notice that these uplink pinnings are done, these server MAC addresses are pinned on the uplinks in a round-robin assignment fashion. Exam time, as you might guess. So how are the server MACs pinned to the uplink ports by default? It's a round-robin assignment by default. Remember, the server interface pinning was going to vary based on the number of links that we use. But pinning on the uplink ports is round-robin by default, or, as you might guess, you as the administrator can go in and manually pin. That's right. You as the admin have control over this. you can go in and manually pin particular MAC addresses to particular uplinks. Now, what happens in a failure with our uplinks? Oh, and Joe's got a great question. What would this look like if you're running those virtual port channels? Same thing. Yep, the same thing. Anytime we mention these uplink ports and the uplink pinning, keep in mind that that could be a port channel. Yeah, great point. So if it's a port channel, it's pinned to the port channel. Excellent point. And remember, the virtual port channeling, that's transparent on the Fabric Interconnect. It just considers it a port channel. The virtual port channel is a trick with the Nexus, and the Fabric Interconnect stays completely oblivious to that. All right. So what happens when one of these uplinks fails? Maybe it's even a port channel that has failed between the Fabric Interconnect and the Nexus equipment. Well, with what we call automatic uplink repinning, the MAC addresses are repinned to remaining uplinks. What the Fabric Interconnect does here, let me draw this for you. So here this failed uplink occurs, and we have these 3 remaining uplinks. What the Fabric Interconnect does is it starts flooding out gratuitous address resolution protocol frames, GARP frames, so that there is a quick relearning or repinning of these virtualized MAC addresses to remaining uplinks. So automatic uplink repinning is the default behavior. By the way, if you lost all of the uplinks on a particular Fabric Interconnect, okay, so we lose all of them on Fabric A, well, everything gets pinned over to Fabric B, and it goes ahead and does the round-robin approach to load balance across those particular uplinks. So pretty cool how this automatic repinning works. But remember, you have the ability as the administrator to override this automatic pinning type behavior. And this is what we use pin groups for. So let's talk about manual pinning, uplink pinning, and what would happen in failure recovery scenarios. So we can create a pin group. Notice when we create a pin group, we're saying, okay, I have some Red Hat operating systems. I'm going to name this the Red Hat pin group. And I am literally going to indicate what uplink ports are my target for this particular entity. So here we have in our UCS system this virtual MAC address. Here we have this virtual MAC address associated with this, sounds like a Red Hat virtualized box. and we pin it to either 1-18 on fabric A or 1-18 on fabric B. We talked about reasons why you might do this in our design course, right? You know, there may be particular security implications, particular reasons why you want to direct traffic flows. You're doing particular traffic engineering in the data center system, okay? And you want to manually pin. You want to know at all times where the traffic flows from particular virtualized servers are going. Well, sure enough, this static pinning would be your answer. Remember, we want controls like this in the UCS system because one of the major disadvantages of the virtualization of this environment, and we already talked about it in this course, is the inability to control the virtualized traffic. It's like you can just, everything is virtualized and you can lose sense for, okay, where is a particular VM's traffic going? Well, if you had a need to explicitly traffic engineer like this, pin groups, static pin groups would be your way to do it. Now, as you might guess in our example, if there is a failure, the uplink fails, Ethernet 1/18 fails for fabric A, then we would have a failover that's automatic to fabric B, but it would have to stay on the Ethernet 1/18 port, which we statically pinned. Okay, great work. Well, the remainder of this chapter 5 is simple because it all kind of builds on everything we just learned, except it's in the world, very similar world, of storage area networking. So let's go ahead and wrap up this chapter 5, which has been just such a critical chapter, hasn't it? Here in chapter 5, we've been talking about the hardware infrastructure and how we cable things. We're certainly talking about some logical configuration elements like VLANs, and now we're going to talk about virtual SANs. But this chapter 5 has really been about, building this UCS system and what our capabilities are. Then in chapter 6, we start all the logical entities, right? Like creating a service profile that'll allow us to quickly deploy a server for a particular job in the unified computing environment. So I know this is a lot of material, and that's why I'm trying to go through it as slow as I possibly can, but yet obviously still cover all the material. We've got a lot of material to cover in the second week of classes as well. All right, so let's wrap up this chapter 5. We better do that. And like I said, this will be simple because it's going to be very much tailoring on what we've talked about, just in a storage area network environment. All right, when we start talking about storage area networking, one of the things we need to consider is fiber channel. Now, fiber channel identifies two types of ports, doesn't it? Well, there's actually many types of ports, but there are two types of ports that we are interested in. There's fiber channel hosts, and those utilize what are called N ports, N for nodes, and then there are F ports, F for fabric. So we've got our N ports and our F ports in a fiber channel type of infrastructure. Exam question time. What type of equipment does Cisco manufacture for the creation of storage area networking? It's their MDS equipment. So when we see the acronym MDS, we know this is the equipment from Cisco for the storage area networking. A whole line of MDS devices. Okay, so here you can see, yeah, I love it. Someone in class, who is that? It's Pete. Pete's getting hungry. He looks at the storage array and he sees a bunch of pancakes. Yeah, I hear you. I'm getting hungry too. So here's our MDS system. And you notice the MDS system is bringing together fiber channel hosts that want to consume this data and the storage itself that has its efficient way to store a bunch of data inside the fiber channel. Now, when you start talking about fiber channel, you realize that there are three basic topologies. The simplest fiber channel topology, but it's one that is seldom ever seen, would be point-to-point. A more scalable type of topology would be an arbitrated loop. But by far, what took off as the most popular topology for our fiber channel storage networks is a switched topology. This is because it's extremely scalable, theoretically scaling to millions of different nodes that could consume the data stored in the storage area network. Notice, in order for this particular switched fabric channel environment to take place, we need a fiber channel switch in order to make that technology work. All right. Now, a key Cisco technology that is going to be employed by our fabric interconnect, and if you haven't, been impressed with the fabric interconnect at this point, you're probably about to become really impressed with it. A key technology that the fabric interconnect is capable of is called N-port virtualization. Yeah, the fabric interconnect can do what's called N-port virtualization, and now we're going to have server interfaces and border interface technologies. So the blade server interfaces can function as our F ports, and the uplink ports from the fabric interconnect to the MDS, as depicted here, can function as what are called proxy N ports, or NP ports, to use the Cisco terminology. Okay, this is some gory details, but all we really need to think about is, okay, what is this gonna act like? Well, it's gonna act like we see here. This N-port virtualization is going to allow, once again, for server links to be pinned to particular uplinks to the fabric switches, to the MDS switches that live off of those uplink ports. Very cool. If you want to get into the details of this N-port virtualization technology, let me show you this slide. Don't be intimidated by this slide. Okay? We don't need to know all this for the exam, for example. But this is what the technology looks like. Remember, those N proxy virtualization uplink ports are here on the fabric interconnect. These F ports are down here on the server blades. And then we know for the consumption of the storage area data, we have these HBAs, the fiber channel host bus adapters. So one of the things that ends up happening with Cisco's N-port virtualization technology is that it is extremely scalable. Yeah, it is extremely scalable. In traditional fiber channel switching environments, we have this consumption of fiber channel domain IDs, for example. And there's only 239 of those that are available for defining domains. So this can have scalability issues. Notice with Cisco's N-port virtualization approach, we don't even consume one of these fiber channel domain IDs with this infrastructure. All right. Let's talk about next up here. We need to talk about virtual storage area network, or vSANs. Now again, the really good news is this is going to follow very closely the logic of our virtual local area networks. So let's talk about exactly how our virtual SANs are going to work in the Cisco UCS environment. Again, similar concept to our VLANs. We're going to go into the SAN tab of the UCS manager, and we're going to globally create our virtual storage area networks. Very similar to our VLANs, we have a virtual SAN that is a default, and by default that's vSAN 1. Notice we cannot delete that vSAN. Just like our VLANs, we can create these vSANs globally or Fabric Interconnect specific. But once again, just like with our VLANs, both Fabric Interconnects will typically share the virtual storage area network configuration. Okay, the uplinks on our Fabric Interconnect are configured as F ports. In other words, the F port here, the port here is an F port. Okay? So just like we had this discussion in our LAN environment, I told you we got to go to the person that runs the Nexus and make sure that's a trunk link. Here, notice the MDS switch must be configured appropriately as an F port. By the way, memorize this. For these uplinks, we have a limitation of exactly one virtual storage area network per uplink. So one virtual storage area network per fiber channel uplink. All right. If we're going to engage in fiber channel over Ethernet VLANs, notice we need to specify the fiber channel over Ethernet VLAN for each of the virtual storage area networks. Notice we cannot conflict here with our VLANs we created for the LAN aspect of our environment. So make sure your fiber channel over Ethernet VLANs are using unique identifiers from your normal VLAN objects. So this requires pre-planning, doesn't it? We want to make sure that we have an unused range of VLANs for use with fiber channel over Ethernet. All right, with all of that said, obviously the graphical user interface work that we have to do here is going to be quite simple. Now that we understand all that, we're going in to the SAN tab, Storage Area Network tab. We're going into the SAN object and we're going to go to the fiber channel uplinks for one of our fabrics, and we use the create virtual storage area network action. This initiates the wizard. We see how similar this is to the virtual local area network creation. Mandatory name, mandatory ID, and then if we're doing the fiber channel over Ethernet here, we indicate the fiber channel over Ethernet VLAN for this particular virtual storage area network. Notice that we have the default, just like with our VLANs, of the common configuration of this virtual storage area network between the two fabric interconnects. Could we do a fabric-only virtual storage area network? Yes, we could. But again, we have issues here with failover. Now, just like with our virtual local area networks and the virtualization here, we were concerned about MAC addresses. Our virtual host bus adapters, they need an abstraction of worldwide network names and worldwide port names. And in Chapter 6, we're going to see how we can accommodate that. We're going to tell the UCS, hey, look, you're going to maintain your own virtualized name database so that once again, if there is a failure of a device in our chassis, we can move these logical components from location to location, and the virtualized worldwide names and worldwide port names can move with them. All right. Well, what about pinning? Well, sure enough, in the virtual storage area networking environment here, we are going to pin for the particular virtual storage area networking. So pinning is going to be based on the virtual storage area network. Notice that server interfaces are only pinned to border interfaces with matching virtual storage area network configs. So if we don't have an interface with a matching vSAN, the link stays down. Notice this particular vSAN 30 here is not properly defined. It is not bound to a particular uplink interface, And as a result, this stays down. This link stays down in the chassis. Okay. For the uplinks, what's going to happen with this concept of uplink pinning? Well, again, it's going to follow just what we saw with the uplink pinning in the virtualized environment. So let's take a look at this. Just like with our LAN environment, these server worldwide networks, these server worldwide names on a particular fabric are going to be pinned to uplink ports in a round-robin assignment. Nothing new to memorize here. So this is nothing new that we have to memorize. Now, if a uplink goes down, just like in our VLAN environment, there will be an automatic re-pinning to our available uplinks. Now, what happens if we have all uplinks on a particular fabric interconnect go down? Well, the operating system or VMware itself is going to have to discover the path loss and reroute. So if you haven't configured high availability inside either the operating system or the hypervisor, then you're going to have a lack of communications. Just keep that in mind. This is obviously a rarity that we lose all our uplinks, but if we haven't configured VMware or the operating system for the cutover, we could have loss of connectivity. Okay, you're not surprised. Then in addition to this dynamic uplink pinning in our storage area networking, we can do manual or static uplink pinning. And we're going to create a SAN pin group. And this is almost identical to the logic for the VLAN, for the LAN pin group that we spoke of. So we can go in and we can say, all right, we have a particular device and we want it pinned to a particular fiber channel uplink. And if there is a failure, we're going to define what uplink on the alternate fabric interconnect that cutover is to utilize.